Hi everyone, I'm Francesco Ragusa from the University of Catania, and today I'm going to present our work EgoExtra, Video Language Egocentric Dataset for Expert Trainee Assistants. Every day, people naturally engage in different activities, such as washing a car, repairing a bike, assembling a new furniture, or preparing a dinner. Mastering most of these activities require time, dedication, and often the guidance of an expert that is able to give to the user practical suggestions that guide the user through the steps. Ideally, a personal wearable assistant should be able to see what the user is doing and relative vision to language to contextualize questions such as what is this or what should I do now? And this personal assistant should, for example, notify the user for dangerous action or performing some activities suboptimally and give suggestions on how to improve. Beyond the visual question answering, able to provide a proactive interaction and support, naturalistic conversations are missing since the state-of-the-art dataset comprises designing synthetic conversation obtained through natural language understanding pipelines or exploiting LLMs, or this dataset contains post-acquisition narrations. Current benchmarks on egocentric vision lack of principal benchmark, including real dual-agent conversations. To address this limitation, we present EgoExtra, a new dataset of expert trainee interactions aimed at validating video language models. EgoExtra is composed of 50 hours of egocentric procedural videos with real trainee expert conversations recorded during the video acquisition process. In EgoExtra, we captured everything that area classes are able to acquire: RGB, SLAM, gates, and poses, IMMU, and so on. And also, we acquired the expert gates during the acquisition. Moreover, we recorded the audio acquisition between trainee and expert, and then we transcribed them. We collected the EgoExtra following the Wizard of Oz paradigm, historically adopted in the dialogue state tracking literature to collect realistic conversation terms between users and machine-like systems enacted by humans. So we designed two protocols. The first one is called proactive and the second one on demand. And for the proactive protocol acquisition, the trainee has not knowledge about the environment, the objects, and the procedure to perform. The expert speaks freely with the trainee, suggesting next steps, instruction, and anything that may be useful. This step is necessary to give a context to the trainee, for example, where are tools, and an overview of the critical steps of the procedure. In the on-demand acquisition protocol, now the trainee knows the environment, the objects, and the procedure to perform. This is the realistic settings that we want to use in our benchmark, and the expert is asked to answer only the questions asked by the trainee. In EgoExtra, we acquired a total of 123 videos, amounting about to 50 hours at 15 FPS. The recorded procedures are split across 10 different activities and 4 scenarios. Data collected involved a total of 33 trainees and 4 experts across 19 distinct occupations. All volunteers will provide their privacy consent and authorization to acquire data in the considered environments using the described protocols, transcribe audio conversation, and publicly release the resulting data for research purposes. Here, we can observe the scenarios chosen to acquire the EgoExtra. The first one is bike workshop, where we saw trainees perform 2 different activities: lubrication breaks and air chamber change. The second scenario is bakery, where trainees performed activities like make tart and make biscuits. The third scenario is assembly, where trainees performed assemble and disassemble a chair and also assemble and disassemble a chest of drawers. The fourth scenario is kitchens, where trainees performed two activities that are make lasagna and make vegetarian meatballs. To generate the QA set, we design a multiple choice QA generation pipeline, which is composed of three steps. In step 1, we extract clean question-answer pairs from the raw transcript. Because conversations are informal and full of filler words, simple heuristics don't work. So we use the Llama 3.1 model to identify trainee questions and expert answers, fix grammar and transcription errors, and generate 4 negative answers for each pair. This gives us high-quality QA sets that is still grounded in video context, since all conversations naturally refer to what's happening in the scene. In the second step, the initial QA sets are validated by humans. 6 expert validators manually review the questions, the answers, and negative examples using a dedicated web dashboard. To help them judge correctness, we also display the original conversation term plus surrounding context. Each QA set could be marked as acceptable, incorrect, transcription error, or needing manual revision. These initial validations were then used to design a scalable process on Mechanical Turk. Only highly reliable workers, those with over 19% acceptance rate and a perfect score on our qualification test, were allowed to participate. Each QA was reviewed by 5 workers, and overall around 25% of the initial QA pairs were filtered out. In the last step, we verify that each QA pair is truly grounded in the video. So trainee expert conversation often refer to actions, object states, or procedural steps that happen visually. So we manually checked each QA while watching the corresponding video clip. Using the same dashboard from used in the step 2, 6 annotators labeled each question as grounded or not grounded, or video contains the answer. So we then scale this process again on Mechanical Turk, and at the end of this process, we discarded 28% of QA. Following the mainstream multimodal LLM benchmarks, we evaluated human-level assistance with multiple choice questions. So the input is the video clip with a trainee's question and the list of possible answers. So we fed the video clip, the trainees, and the possible answers to the models, which should predict the correct one. To obtain a human baseline, we also collect a survey, providing also the video clip to contextualize the trainee's question. In this way, we obtain the human baselines that we can compare with our MLLM models. We consider 4 representative multimodal large language models as baselines, and also we include 5 LLMs to assess the ability of current models to infer the correct answer purely from text. Looking at model performance, language-only models perform very poorly, close to random guessing at around 20% of accuracy. Video language models do better, but still only reach around 30% on average. The top performer is Lava 1 Vision, with an accuracy of about 33%, outperforming the other baseline. Still, even the best model reaches only about 1/3 accuracy compared to humans, who achieve almost 90%. So there is still a very large gap between current models and human performance. To conclude, in this work we introduced EgoExtra, a new egocentric dataset designed to evaluate intelligent wearable assistants that provide natural language guidance in real-world settings. Using these conversations, we built a challenging VQA benchmark and evaluated a wide range of LLMs and multimodal models. Our results highlight 3 key points. The benchmark is difficult for current systems, text-only LLMs have clear limitations, and contextualized video input significantly boosts performance of LLMs. Both the dataset and the benchmark are publicly available. Thanks for the attention.